Welcome to the 8th week of the course Collaborative Robots Theory and Practice. This week we'll discuss on force control of serial chain robots. Using force control, we enable the robot system to handle compliant robotic tasks. It uses the principle of robot dynamics and control. With the background that we have developed in the previous weeks, we are now ready to study force control. So let us start with the first lecture of this week, that is on external force control loops and admittance control. So in this lecture, I will be discussing on force control. I will just introduce you to that. We will see force control with external force control loop. We will see what is admittance control. We will discuss merits and demerits of external force control loop and admittance control. Later, I will create a 3R spatial arm as a test model for force control implementation in MATLAB Simulink environment. Okay, so let us begin. So what is force control? As you have already seen in my earlier week, that is on week 1, I have showed you various applications of force control, that is through assembly operation, manipulation, manufacturing and robot human interaction. Those were the applications of cobot. So how that is done? Those were all done using robot force control. Force control involves robots sensing and responding to any external forces and moments, which allows for precise manipulation and interaction with the environment. Now what is active, what is passive? Passive is the one that I have used with the springs at the end effector or some spring like structure at the end effector, which can also do some compliance at the end effector beyond the robot flange. Okay, that is a spring like structure fitted between the gripper and the robot flange. So there is that compliance structure allows some sort of disturbances or any kind of external force jerks to be taken up by the robotic system. Okay, but yes, rest of the robot remains stiff. So that was passive control. In active control, we take care of live forces from the end effector or sometimes from the joints also, force and the torque, and includes that in its control loop to do compliant manipulation. In that case, whole of the robot structure becomes compliant. Okay, so we'll discuss on active force control in this module only. Okay, the benefits are precision, safety and adaptability. In general, any control structure would look like this. Okay, you see you have some desired position or force commands over here. You have a comparator which keeps on checking the desired value and the actual value which comes from the sensors. Sensors with feedback elements gives you that. So it compares that, calculates the error, sends it to the controller, and finally it goes to the power amplifier and to the actuator, and actuators are fitted to the manipulator, and finally manipulator gives you the motion. Any disturbances or uncertainties are taken up by the manipulator or by the end effector of the manipulator, and it does precise manipulation. Okay, so this is the general structure of any control algorithm. In case of force control, we restrict the commands to be position and forces only. Okay, so this will be the structure of that. So that is what is the robot force control. Okay, now let us discuss what is active force control with external force control loop. This was long back proposed by Shutter and Brussels. It was proposed in IJRR journal, International Journal of Robotics Research, in 1988. It proposed using a force sensor. So this is the typical structure of such system. Okay, you have a robot arm. Here it is shown as KUKA KR5 ARC robot with a force sensor over here. Okay, and you have the gripper. It may be a gripper, it may be a grinding, polishing or any other tool. Over here it is a gripper. So that is the tool to be more specific. Okay, and you have force sensor in between the robot flange which is here and the end effector tool. Okay, so this is the force sensor. So it checks the live forces. While it does any job, it checks the live forces, and those forces are now included in the external loop apart from the position control loop which is already there in such robots which does precise positioning. You bind an external force loop to control the forces at the end effector. Okay. So you see, this is the control structure for that. Okay. So you have desired force that should be there at the end effector, and it continuously monitors the force through the sensors, sends you as a feedback here. Okay. Calculate the error, sent to the controller here. This is the transfer function for the controller. Controller sets the reference trajectory in terms of position to the robot arm. So this is standard position controlled robot which takes in the position trajectory here and gives you the end effector position. Okay, so this is a comparator. Basically, this is in case of a live robot, you can directly get the force sensors which are through the force sensor fitted at the end effector. But in case of simulation, you may require to calculate it using the environment position and the robot position, calculate the error and stiffness of the wall or the obstruction is put here, so that Ke into x minus xc, that is robot position minus environment position, multiplied by Ke gives you the force. Okay, so this is the general equation for interaction, wall interaction or any interaction, and it gives you the force feedback. Okay, so this is only in case of, whole of this is only in case of simulation, but in real case robot directly gives you the position and you directly get the force feedback to this loop. Okay, so this is the general structure of such active force control using external force control loop. Okay, so this is implemented by creating an external force feedback over a position controlled robot in task space or in tool space. Tool has its own frame. Okay, in that frame also it may be achieved, or in robot Cartesian space it can be achieved. Okay, any existing position controlled robot can be retrofitted. This is the beauty of such compliant manipulation algorithms, that you can just have a force sensor fitted at the existing robots in the assembly line or in any application, and you can convert it to do such compliant manipulation task. Okay, it gives you improved safety, precise assembly tasks can be done, adaptability to any uncertainty which is there through robot vision or through robot accuracy. Okay, so it can take up those uncertainties. Okay, enhanced interaction, it can be more interactive, cooperative manipulation, surface finishing or any other collaborative manipulation tasks. Okay, the only problem here is the collision with the links remains undetected. Okay, the link collision cannot be detected because there are no sensors which are in the rest of the robot. Okay, so whatever happens, it happens beyond the force sensor, and those are sensed by the robot, and that can be considered in your closed loop. Okay, apart from that, they are slower in response. That means because this robot has an external loop and the forces, the error is considered by the robot's controller using this controller signal. So this controller essentially remains outside the robot controller. Okay, you have position control which is inbuilt to the robot, but this controller, force controller, remains outside to the robot. So there is a communication, continuous communication which is happening here, and that communication and doing this closed loop has some latency there. Okay, so that is the reason such control is very much slow. It is not very much in real time. Okay, so let us just see a small video on that. So this is what I am doing. I have just fitted a end effector, rest force torque sensor at the end, and it is checking for forces from all the three directions. I am able to move the robot. If I have limited it to 10 Newton in all the three Cartesian directions, so anything greater than 10 Newton will start making the robot move in one of the corresponding directions. That is what is happening here. I am able to drag this robot to anywhere I want. Okay. Okay. So this is external force control loop. Okay. So now admittance control. This again is an explicit or direct force control where you directly command the forces, or in general the wrench. Wrench is a 6x1 matrix which is essentially contains the moments and the forces at the end effector. So that is there. So in general we talk about moment and forces, but normally we use forces. Okay. So admittance is defined as the inverse of impedance. Okay. So twist is equal to admittance times of wrench, that is the measured wrench at the end effector. So you have measured wrench given by WE, T is the end effector twist, twist again is the 6x1 vector of angular velocity and displacements, A is the diagonal matrix of admittance. Okay. So when you see twist is equal to A times of WE, okay, integrating the twist should give you the positions, okay, because those were the velocities. So integrating that gives you the position. So admittance times of wrench desired minus wrench actual. So again this is a closed loop which takes in wrench desired and the feedback input, that is wrench actual, measured wrench, take the difference, calculate the wrench error into the multiplied by the admittance gives you the twist vector, and integrating that gives me the position trajectory. So this position trajectory after integrating here is sent to the robot controller as a reference trajectory. Okay. This is the second input. First input is the wrench input. This could be the second input which also takes in the position trajectory here. Okay. And this is the actual position. Okay. So final desired pose input, okay, the final desired pose input is QD, okay, QD minus QA, that is the actual position, and the reference trajectory input. Delta Q that comes here, this is delta Q. What is delta Q? Basically it is the difference between the Q desired, that is the trajectory, that is desired trajectory, QA, this is the reference trajectory which is set by the admittance controller here, and Q is the actual feedback. So if you take the difference you get a change in pose which should happen due to the admittance controller and the trajectory inputs. Okay. This is sent to the Jacobian inverse. Finally it gets converted to the joint space multiplied by proportional gain which is here gives you the torque trajectory. Okay. So tau A is the torque which goes to the robot controller once again, and again over here you have tau G. This essentially is the gravitational compensation torque which makes this robot free from the gravitational pull, okay, and robot becomes floating in the space, as we have already discussed in the statics module that you have seen. So tau G essentially makes the robot floating in the space so that controller becomes free of gravity. Okay. So that is there. Now you have, this is the twist which is sensed or calculated by the robot forward kinematics. So that is the end effector twist. Twist multiplied by Jacobian inverse gives me the theta dot times, and theta dot, that is the joint rates multiplied by the viscous friction which is there at the joints, should give me the torque due to the viscosity or due to the damping which is there at the joints. Okay. So this is what is realized only in case of simulation. So this loop is there for simulation only. In case of real robot, you don't need to calculate the viscous or damping torque. Okay, that is automatically there within the robot. Okay, so tau v is there in case of simulation. Similarly, it is calculating the torque due to the forces which are felt at the end effector. So robot position minus environment position multiplied by the stiffness of the environment gives you the wrench due to the environment interaction. So this wrench multiplied by Jacobian transpose gives you the torque due to any environment interaction. This again is a direct case. In case of a robot, a physical robot, you need not to calculate. So all the yellow blocks, this one, so this is only there in case of simulation. In case of real robot, you need not to worry about. Okay. So this is how this admittance controller would work. So all the elements, I hope it is clear to you. So this is tau A is sitting here, tau A is kPa, that is the proportional gain times of delta q Jacobian inverse, it is here. So this equation sits here, and this one is from here to here, Wd minus We A integrated, so it is here. Okay. So this is how it is a dual loop again. So you have We, which is set as a feedback which is sensed through the external force torque sensor. Okay. So again you are depending on external force torque sensor. Although the robot is a torque controlled robot, so in this case robot is also compliant because it is sensing the end effector force torque using this, and also the joints are compliant because of torque driven robot. Okay. Torque is exactly whatever is required, so the robot becomes compliant to any external force which comes on the link. There is a problem, you also need a external force torque sensor. The beauty here is it is a direct force control technique, so you can directly precisely put the force commands and it exactly achieves the precise force at the end effector. It is very beneficial for applications which requires precise force control. Okay. So compliant manipulation with precise force control. Let us start preparing 3R special arm for simulation of force control algorithms in MATLAB Simulink environment. Why I have chosen 3R special arm here is because most of the industrial robot or a cobot are also 3R special arm right up till its rest. Okay. And special arm can attain any position in Cartesian space in x, y, z location. So that is the reason I have chosen this, and to make things very simple, I have chosen just a 3 degree of freedom system which can move along x, move along y and move along z, that is in all the 3 directions. So I can control my forces in all the 3 directions. I am not talking about the moments here. To make things very simple, the prerequisites here would be MATLAB with any standard Simulink environment, any version of MATLAB with standard Simulink environment. I would require Simscape multi-body toolbox to create my robot and do my closed loop operations. Additionally, you can have, this is optional, robot system toolbox which can take care of gravity torque, or it can calculate the robot Jacobian and all. So that becomes very trivial in case of robot system toolbox, but that can also be done programmatically when you are using multi-body toolbox. Okay. So you may refer to this paper that I have cited here, that is simulation of force control algorithms for serial robots by me, that is IEEE SII conference publication that you can go through. Okay. So let us have some background on 3R special arm that you already know. I'll directly show you this video, kind of motion that it can do. I'm moving joint 1 here. Okay, this is joint 1 motion. So first axis is perpendicular to the ground and it is along Z axis. XY plane is the ground plane here. Okay, the joint 1 is done. This is joint 2, which moves link 2 and 3 simultaneously. Okay, this plane of motion is perpendicular to the plane of the ground, that is the surface on which this robot is mounted. And the third joint is also like that. Okay, this moves link 3 only along with it, and this also is in a plane which is perpendicular to the ground. Got it? So this is how it is going to move. So I assume the links are all slender. It is ideal slender link with mass center location at its center. Okay. All the center of gravity location is precisely as it is at its center. Okay. So Jacobian can be calculated. You already know how to calculate Jacobian. Same way you can arrive at this result using the techniques that was discussed in robot Jacobian and velocity kinematics. Okay. Gravity compensation can be calculated tau g like this. Okay, that was also discussed in robot statics module. Okay, so these two I have directly put here. I will be using these to calculate the gravity compensation torque and the robot Jacobian directly when I will be doing these calculations in MATLAB code. Okay, interaction model I have taken it like this. So robot's end effector position is here. Okay, and this moving obstacle or obstacle is somewhere here. So whatever is the robot movement into the obstacle, so whatever is the penetration that happens into this obstacle, so that is calculated using x minus xe. X is the end effector coordinates, that is calculated using robot forward kinematics, and xe is the position of this moving obstacle. Okay, so difference between them should give me the amount of penetration of robot's end effector that has happened into this obstacle. So that is actually the compression which is happening to this obstacle. So that compression multiplied by the stiffness of the obstacle gives me the forces. Okay, so if this is an obstacle, okay, due to any robot's movement into that, so you get what? You get some deformation here. So this deformation into the stiffness gives me the force that is generated. Okay, and this force is normally along the direction which is perpendicular to the direction of this compression. Okay, so whatever is the deformation, it is perpendicular to that plane. Okay, so that is how it is assumed. I haven't assumed any frictional forces that may also generate due to movement of the robot along the plane of this obstacle. Okay, that I have ignored, but yes, normal forces are generated due to the compression of the obstacle. So this is what is the interaction model. So hope you have understood it. So now I will create 3R spatial arm. Let us see the demonstration of creating the 3R arm in MATLAB Simscape with multi-body toolbox, also using robotics toolbox which is optional. Okay. Let us switch to MATLAB now. Okay, so this is my MATLAB environment. I can get into the Simulink directly by pressing it here, okay, or double clicking the model that I have generated. So I'll do that now. So this is my MATLAB Simulink environment, okay. So you have a library browser where all the tools are there that we have discussed earlier in one of the modules also, okay. So this is the 3 arm that I have built earlier to save some time. So I will directly touch upon the various blocks that I have used here. I have used the solver configuration. You can insert this directly here, double clicking on the space, type solver configuration. So you can directly get that in the utilities here. So you can take that from the utilities here. From utilities you can directly drag and drop. There you get the robot solver configuration. So this is the block that is there in the utilities, okay. Again, world frame I have inserted here. You can directly go to the Simscape environment, multi-body, and utilities. You get mechanism configuration, that also I have used here, okay. So this is my mechanism configuration. Frames and transforms, here you get world frame. So these are the blocks that I have used. So world frame, this also can be used directly from here. World frame, so you can directly click here and you may get that inserted here. This is already here, so I am deleting that. So this is your world frame. This actually says the 000 position, that is the reference position of for whole of the robot's representation, okay. This is the solver configuration. This is mechanism configuration. This also says the direction of acceleration due to gravity. So now I have 0 minus 9.8. So that means 0 along x, 0 along y, and along z, that is the perpendicular to the plane of the surface. You have acceleration due to gravity that is directed downward, as I have shown in the 3R manipulator also. So acceleration due to gravity becomes along minus g direction, okay. So that is there here once again, okay. So this is my this becomes the skeleton for any model that I will be making. So these three blocks are always there, okay. Now I start with the first joint that will mount link 1 on top of that, okay, the way it is here again, okay. So you have the first link, that is the violet color one, which is mounted on top of the frame 0, that is the ground frame, through joint 1. So here is your joint 1. Joint can be found here, okay. So you have all the joints. So I have dragged in the revolute joint. This is the revolute joint. This revolute joint I have used here. You can directly click here and type. So now you know, you can directly type it here if you know the toolbox, if you know the block name, okay, or you can directly select from here, okay. You can choose one of them and you can directly drag and drop and you can get to that joint, okay. So this is the joint 1, okay. So that I have inserted here. Now joint 1 has B and F. You can read it. This is B and this is F. B means the base, F means the follower. So base is joint, base is connected to the world frame, follower will contain my link, okay. So this link, again you can have various body elements. Body elements here I have chosen brick solid, it can be cylindrical solid or anything, okay. So this is my brick solid element which is here, okay. So now this I have dragged it, but I have to model it also. I have to give it some length. So double click on it to select its property, okay. Dimensions are 0.01. If you see 0.01, that is along x. So this is my link. So along x it is 0.01. So it is, I want to make it very much slender, okay. So this is the reason I have taken very negligible dimensions along x, similarly along y. Along Z, that is along this direction, okay, length of the link I have kept it as 1 meter. 1 meter. So the total length of this is 1 meter. Okay, now the inertia property I have chosen calculate from geometry. Density I have chosen, or you can directly key in the custom mass or the point mass, you can directly key in here. Okay, again density it will calculate based on that. Okay, so this is very much useful to calculate moment of inertia and other factors which are there. So if you say it is a custom one, then you are asked to insert the mass of the link, center of mass location, moment of inertia, that is Ixx, Iyy and Izz, those, or and product moment of inertia can be inserted as well. Okay, so this is using custom way, but I have kept it as default by using geometry here as default. Okay, and I have just put the density, so it will automatically calculate those parameters, and the total mass center, it will assume it is evenly distributed mass, and that will be there. Okay, graphic location from geometry, visual properties you can choose. I have chosen red color here. Opacity is 1, it can be opaque, it can be transparent, semi-transparent or something like that, but that I haven't touched upon, just chosen the color here. Okay, frames, there are 2 frames, one of them connects this to the link to the joint. Okay, that is over here, that is at the bottom of this link. Okay, that is frame 1. So that is chosen like this. So this is your space where you can select the link also. So again now you can do pan, zoom, something like this. Okay, using shift button and mouse center button I am doing the panning operation, or you can do scroll button to just zoom in and zoom out. Okay, so panning, zooming in and zooming out, select to certain standard views from here. From the toolbox you can do completely fit, isometric, different views can be done. This is how you can manipulate your object which is there in this workspace. From here you can directly select the front view, okay, isometric, top view, left view and something like that. Okay, so this is how I am doing it. Okay, so now you see along the length of this link I have Z axis. Okay, because I want to rotate this link about its own Z axis, so the joint will come here, the joint will connect this. Okay, so it is along Z axis. Okay, and other 2 axes are here, so Y is aligned along Y, X is aligned along X, Z like this. Okay, so this is how it is. Okay, now the frame 2. So yes, again in frame 1 also you see Z is primary, Z is aligned along principal axis Z, secondary axis is, if you select 2 of the axis, the third one gets calculated automatically. So if you select X axis along plus axis, so this is the default, I haven't touched upon, so that became my frame 1. So now going to frame 2. Okay, this is how I want my frame 2 be. Okay, why? You know, because the next link which is there, it is like this. You see, as per the DH parameter, Z axis should be like this. So I have to rotate this Z axis. It cannot remain aligned with the principal axes which are here. Okay, you have to rotate it because you want your DH parameter to be set like this. Okay, so all the rotation, this revolute joint rotates about Z axis. So I have to put it like that. Okay, so this is the reason Z axis is like this. Okay, so now I will rotate the frame which is by default, which was there. So by default it is aligned with the principal axes which are here. Okay, so I have to rotate it like principal axis was along Z, so that will now be along plus Y. Okay, so you see my Z axis principal axis is along y axis. Again, the second one, secondary axis is principal axis y, principal axis y, you saw it is z axis, now it is secondary axis plus y is along minus z. So, plus y, this green color which you can see here is along minus z. Okay. So, now two axes are defined, third one, that is x axis, comes directly along x axis. So, this is how it is. Okay. This you know, you have to have the z axis along axis of rotation of the revolute joint. So, that is the reason, based on DH also, it has to be like this. I have rotated it like this. Okay. So, I have put the second frame here. Okay. So, that is my link 1. Now, I will put again joint 2. Okay. Joint 2 is here. Any joint you see, it has state targets. State targets means the value, specify the position of the initial position of this joint. So, that will come here. Okay. Limits, if any, you can specify lower limit, upper limits of the joint rotation. Actuation can be torque, it can be provided by the input, and motion gets automatically calculated. So, torque provided and motion getting calculated automatically, that means MATLAB does the forward dynamics here. So, you see torque provided by the input, motion can be calculated, or it can be otherwise, motion provided by the input, torque getting calculated automatically. So, it is inverse dynamics. Okay. So, forward or inverse, you can do it here. Sensing, you can sense the joint position, joint velocity, right? Acceleration, actuator torque, lower limit, upper limit torque. So, these are the senses which you can have. Normally, we would require the position and angular velocity of the joint. Okay, that will require to be sensed to calculate Jacobian, to calculate the joint angular position, right? We may require actuator torque also. Okay. So, these things we can do to the joint. Now, let us make the, I will calculate it, torque I will provide none, motion getting automatically computed. Okay. So, this is the default setting, I have put it here because this is the initial arm, okay, joint. And then link 2 we have built here. Okay. So, again you have, that was the link 1 end, now gets connected to the link 2. So, over here again you have to choose. So, inertia properties I have set it, left it as it is. Okay. Dimensions again I have kept it as 1 meter, along x, along y, it is negligible dimensions. Frame 1 is something like this, you see. Frame 1, you have axis of rotation, that is z is along this direction. Okay. And frame 2, again you have so that becomes my axis of rotation, that is again along z axis. Okay. Because over here the axes are perpendicular to the link lengths. Okay. That is for the link 2 and final link, that is link 3, both would be very, very similar. So, for both of them I have just kept as it is. So, you see z is directed along positive x, okay, y along negative y, and x along positive z. So, this is the setting for this configuration, okay, that I have kept. Okay. So, this is my link, and third link is exact replica of the second link. Okay. So, that again you can directly copy or paste, or you can again recreate it, is up to you. Okay. Now, everything comes in a series way. It is a serial chain robot, so it is like this. So, you have solver configuration, world frame and mechanism configuration. Here comes your joint 1 with the perpendicular to the surface, there is a link. You haven't edited frame 1, just frame 2 needs to be edited, that has to be kept. parallel to the ground surface, okay, axis of rotation, okay, and joint 2 is here, and link to axis Z should be along the axis of rotation, okay. Then comes joint 3, link 3 is exactly similar to link 2, okay, and this is your frame 2, that is the end effector frame here, okay. Now there is a block which is known as a transform sensor, that also can be introduced from here directly, okay. So if you can directly click here and say transform sensor, so that is there in the multi-body again, okay, frames and transforms. So you can go here directly, multi-body frames and transforms. So here is your transform sensor. This basically does the forward kinematics and lets you know all the end effector transformations with respect to the base transformation. So over here I have selected the base to be the 000 frame, the first frame, okay, ground frame, and the end effector frame I have selected the tip of the last link, that is frame 2, as the follower, base and follower. So in between them it will calculate the transformation. So you can get the angular velocity of the end effector, angular acceleration, translation along x, translation along y, translation along z. So you can get all the forward kinematics computation using transform sensor, okay. So it gives you that. So now I am just choosing to sense the translation along x. Always remember, all the system here uses a data format which is of physical system data format, and by default Simulink uses a different data format. So you have to convert the data, okay. So there is a converter called as Simulink to PS converter and PS to Simulink converter. You can directly insert it from here, PS to Simulink converter. It is there in the utilities. So here you get it, Simulink to PS and PS to Simulink block, okay, these are there, okay. Using that you can convert that so as to see the plot. So plot is there, this is the scope where you can see the plot of x while this robot moves, okay, x coordinate of the tip where you have put the sensor here, okay. So Simulink in the sinks, so everything which is terminating, storing the data, displaying it, plotting that, so everything comes here. So these are the sinks, okay, and there are sources also. If you want to generate any signal, these are the sources. So this is the sink that I have introduced here. So that is a scope, I want to see the plot, okay. Because this is a general Simulink block, so you need to convert the data from physical system to Simulink. So now I am ready with the 3-link system and I can simulate my robot. So you can directly run it from here. Okay, so it swings immediately. This is again, this is the workspace where you can see the robot animation here, zoom it, pan it, you can do anything from these blocks, see the default views, okay. So now I am ready with the model in which I can put all the parameters, all the control parameters, create the control loop with this robot and I can simulate that. So this is my robot which is now ready for simulation, okay. You can see the plot here also. This is how it has moved. You could have sensed x, y, z all and see the plots. So this is how I have prepared my robot, okay. Okay. So now you have seen introducing the world frame, joint blocks, multi-body body elements, multi-body frames and transforms, transform sensors, Simulink converters, okay, Simulink sync and scopes, okay. So using this you have now created a 3R spatial arm which is ready to be simulated, okay. In later, we'll also see demonstration for calculating and testing the robot Jacobian that I'll be doing in the next module. Okay, calculating and testing the gravity compensation torque. Okay, using MATLAB embedded code and also using the robotics toolbox. Okay, I'll be implementing environment interaction model. All this I'll be doing in my next lecture. Okay, and finally I'll test the arm in open loop positioning and do free fall forward dynamics simulation. Okay, so that's all for this lecture. So in the next lecture I'll be doing all this. That's all. Thanks a lot.